welcome to this episode. In this video, we're going to take a look at how to properly split your data set so that you can use a part of it for training and then another part of it for evaluation. And if you watch the previous episodes, I kept repeating the fact that it is improper in the practice of deep learning to evaluate the performance of your model on the same data set that you are using to train it. And the reason is that you are basically tuning the weight of your matrix based on this training data. And so the weight are adjusting themselves in such a way that they will be able to properly make predictions on the training data set. So it doesn't make sense to use the same training data to evaluate how well your model is generalizing, because the whole idea of a deep learning model is to learn patterns from the training data set and generalize these patterns onto never seen before data sets. So you basically train your your model on the training set, and you evaluate on something that we call the test set. And the test set is a data set that is similar to your training data, but then it is made up of entirely different training examples. And so that is what measures the generalization capabilities of your model. Let me give you a real life example so that it makes it more concrete for you. So let's look at a scenario where a teacher uses an example, let's say 50 times in class, and also examines the students in the final examination using the same question. Basically, if you repeat something several times, you get to the point that your student will be able to form associations between the questions and the answers without actually learning anything. Okay, it is similar when it comes to deep learning. Don't forget that we ran this for a number of epochs, and in the last video you saw that we basically trained for about I think 50 epochs or so. Yeah, 50 epochs. But in a large scale machine learning project, you train for more than 50 epochs. And this gives the neural network the capability to memorize without actually generalizing. And that is why we don't want to use the same training data as the data set on which we evaluate the generalization power of our model. So in this case, I'm talking of the perceptron. And scikit-learn, which is also one classical machine learning library, which is very common, gives us a function that we can call to split our data set into training set and then test set. And so that is what we are going to use. And then we will be able to split our data and evaluate on the test set. So basically, I'm going to copy the import here and include that into our own notebook. And so the function is called train test split. And whilst we wait for the notebook to run, I can show you the documentation. It says it splits arrays or matrices into random train and test subsets. Okay, so what happens is you give it your training data, both the features and the target labels, and the train test split function in scikit-learn is basically going to shuffle your data and then split them. It's going to randomly split them into two groups, the training set and the test set, so that you can train on the training set and then you can evaluate on the test set. So I load iris. Everything here remains the same as we did in the previous videos. What changes is before we use it in the perceptron, we are going to split into training and test set. Okay, so I think this is the point where we want to do the training and then the test splitting. And so the functions API says that you give it your features, the target, you specify a test size, that is a percentage of the data that you want to use for testing. And you can set a random state so that if I set a random state of 42 and you also set it to 42, we are basically going to end up with the same train test split. It is not a required parameter anyway. And you can also pass shuffle equals true or false if you want to shuffle. And it's good that you shuffle so that you don't end up with split where the training data set has one particular class and the test set has another class. They need to have equal representations in both of them. Okay, so I'm going to do my split, and it returns x train, x test. This is the features for training, features for testing, target for training, and then target for test. Okay, so I'll come here and I'll say x train, x train, x test, y train, y test is equal to train test split, and I'm going to pass in our x, our y, and I want the test size. So test size, I think, let me cross check. So it is test size. Okay, let's use 25% for test size, and let's say shuffle is equal to true. Okay, so now we have our S test, Y train, Y test, and then S train. And if you want to print them out, you can also do the same. So I'll just do print S train dot shape, and I'll print Y train dot shape, and I'll do the same here. Print S test dot shape and Y test dot shape. Okay, so let's see what happens here. So you can basically see that the training features has 75 data points, and they have two columns, just as you know from the previous episodes. And because there are 75 rows, there need to be 75 targets, and the test set is made up of 25 because we specified that it should be 25%, and this x here is basically made up of 100 rows. So that is what the train test split function is doing for us. Okay, so now that we have our train test split done, what are the changes that we need to do in our perceptron to make it work properly? The first thing we need to do is when we call train, we don't just pass it input data and target data. These used to be the full training data set that we used. Unfortunately, it is on this same data set that we tested for accuracy of our perceptron, which is wrong. So in this case, we want to pass it our S train, our Y train, our S test, and then our Y test. And you see how we're going to use this. So I'll pass in the S test, S train, and then we pass in the Y train, and then we will pass in the S test, and we will pass in the Y test. So we're going to pass in both the training data and the test data, and how we use it you will see in a few seconds. Okay, so at this point, instead of zipping on input and target, we are going to use the S train and the Y train. So I'm going to copy S train, put it here, and then I'll put Y train also here. So we call prediction data, we pass in our target. Okay, so everything looks good up until this point. And what we want to do is we also want to measure the model's accuracy on the training data set as well as its accuracy on the test data set, because there is a concept called overfitting and underfitting, which we'll be talking about. So I'm going to call this train accuracies, and then I'm going to create another one called test accuracies. Okay, so at the point where we evaluate our accuracy, like the model's accuracy, we first of all want to evaluate it on the training data, which is the X train and the Y train, and we also evaluate it on the X test and the Y test, because we want to know how the perceptron is performing on the training data set as well as on the um, test data set. So I'm going to call this um, train ACC, okay, and that is going to call the accuracy, and then we are going to give it X train, and over here is going to be Y train, and then we will also call the accuracy method again, and this time we are calculating the test accuracy. So it's going to be self.accuracy, and over here we pass S test and then Y test. Okay, and then this is the point where we append each one of them to their respective list. So we say train accuracies dot append then we will append the train accuracy here, the train ACC, and then we'll do test accuracies dot append, and then we'll do test ACC over here. All right, so if you like, we can also update this information that we print during the training to include both test and train accuracy. So I'll say train ACC, and for that I'm going to put in what we got for train ACC, and I'll also print out the test ACC. That is going to be test ACC. Okay, now you can see that we have both train ACC, test ACC, and we also have losses. So now we have about 3 items that we want to return after training. And so the best way to return it is going to be a Python dictionary. Okay, so instead of returning a tuple here, what we're going to do is we're going to return a dictionary which will have losses, and then the losses is going to contain the losses list, and we have train accuracy, which is going to have the train accuracies list, and then we also going to have the test accuracy, which is going to have the test accuracies list. Okay, so we're going to return this dictionary that contains the losses, the train accuracies, and the test accuracies for all the epochs of training that our perceptron had to perform. So at this point, after training, we don't get just the losses and accuracies. We're going to call what we get as history. Okay, we get a history, which is the dictionary that contains everything that we return. So I'm going to run this cell, and yeah, and then at this point we can perform our training. Let's see if everything is okay. So it's saying train. Okay, yeah, so we call train and then we pass x and y, even though we have changed the signature to take s train, s test, y train, and then y test, which we have created up here. So we have x train, x test, y train, y test. So this is the order is we pass in the x train, the y train, x test, and the y test. So we pass in here s train, y train, and then we pass s test, and then y test. Okay, now let's run our algorithm, and you can see that the perceptron is actually performing well on the test set. It is performing very well on the train test, on the train set, because it is getting everything correct 100%, and it's also scoring 100% on the test set. So this is what makes us know that indeed our perceptron has learned to generalize to data that it has never seen before. The reason is that the test set that we gave it wasn't used in updating the weights of the perceptron. Okay, the weight updates are done based on how it performs on X train and Y train. You can see that we don't use S test and Y test to update the weight in any way. All we use the S test and the Y test for are to evaluate the generalization power of the perceptron on never seen before data. And so scoring 100% on the test set actually makes us know that our perceptron has learned well enough, and it is going to do well on data that it has never seen before. So at this point, let's learn how we can plot um, graphs for the various metrics that we return from the perceptron training. So at this point, we plot losses here, but don't forget we don't have losses anymore. Instead, we have history. So what's going to happen is we need to read losses from history, and because history is a dictionary, this is how we're going to read it. Okay, okay, so we've plotted the losses here, and we are also going to plot our accuracies here. So what we're going to do is say history, and then we're going to plot accuracies from it. Okay, so we plot accuracies from our history, and I think we should be able to plot it all if we like, instead of what we did in the previous example. And because we have the test accuracy and the train accuracy, it is good for us to plot both of them. Okay, So what we are going to do is, first of all, I'm going to run this so that you see what I mean. Okay, so I'm getting an error, accuracies. Okay, so I didn't call it accuracies. I think it is train accuracies. I think so. Okay, train accuracies. Oh, what did I call it? Okay, train ACC, sorry. So we plot train ACC, and basically it is showing that this looks like a straight line, but it's actually not a straight line. Let's plot up to like the 20th and see how it performs with that. Okay, it still feels like too much in there. Let's do 15. I just want a graph that shows you how it rose. Let me retrain again until I get a graph that is good enough to communicate what I'm trying to show you. Okay, so I think this is good enough. So this shows that our loss fell from 35 all the way to 30, and that actually happened before even the fifth epoch, and that is why when I plot the accuracy previously it looked like a straight line, but the truth is because of the scale you don't actually see that it is rising. Okay, all right, so now we have plotted the train accuracy. What we can also do is to plot the test accuracy. And to do that, I'm going to give this a title. So title, I'm going to call it train ACC so that we can distinguish it from the test accuracy. Okay, and I'm going to plot test accuracy here. The test accuracy, let's plot that in maybe green. Call this test accuracy, and then I'll say ax2.legend to put a legend on the graph. And okay, I think it's label instead, sorry. This should be label, and this should be label. And if you want to learn Matplotlib, I suggest that you watch my Matplotlib playlist. So basically you can see that we have a test accuracy and we have a train accuracy which performed well enough, and so it is hard to tell one from the other, but you can see there's a blue line here and there's also a green line that represents the test accuracy. From that point onwards everything remains the same. So you can run the training multiple times to see how different graphs are going to pop up, and for this you can see that the training accuracy started off at this point, and then the test accuracy started off, and then it rose up onto the point where they were all 100% accurate. So feel free to play around with this notebook and try different ideas out. You can create your own data set that has two features, two columns, and then you can run this training of the Perceptron to see how it performs on your new data set. Basically, what you need to ensure is that your data set is linearly separable. Otherwise, this Perceptron is not going to work. And if your graphs are looking like this, you want to check your scale, because there is no way it's going to start out 100% accurate. It is the scale that makes it look that way. Maybe let me try to train a little longer and see if that is going to change anything. Aha. So now you can see that the test accuracy is 96. So this is also a confirmation of how stochastic training your models are. Like, running the same model twice doesn't guarantee the same output. So now the model is able to classify every data point in the training set, and then it is only able to classify 96% of the test set. And this is actually something that happens a lot in reality. So when we plot this graph, you can see from here, this is your test accuracy, and your test accuracy seems to plateau below the point where the training accuracy plateaus. And this is acceptable. We have 100% on the test, the train data set, because that is what we use to adjust the weight. But then we have 96% on the test sets, which is okay. But there is a phenomenon called overfitting, which I will talk about. And overfitting basically means that your model, instead of learning to generalize, it memorizes pattern in the training data set, and so it is not able to classify well or perform well enough on the test set. And if that was happening, you could see that the test accuracy will be way below the train accuracy. So thank you very much for watching. Don't forget to subscribe, leave your comments, and if you have any challenges, let me know and I'll address them. So I will see you in the next video.